think since everybody's here, we can start now, Mr. George. Before we start, I would like to introduce Mr. George, who will present the topic of the Lidar scan to Revit model as a use case in the TTSH project. We present Mr. George. Thank you.
Just give me a second. Hopefully this works. Okay, let me share my screen.
Yes.
Content. Oops. Can everybody see that?
Yes, Mr.
Okay. All right, everybody. Thank you for your time today. Really appreciate the opportunity to share a little bit about Lidar technology, a bit about BIM, and how we combine the two to create a final sort of Revit model that we have done for the Block 505 over at your project in Navina. So a little bit about myself. Sorry, before we go on to about myself, what I'm hoping to achieve today in the next 1 hour is hopefully to give you a basic understanding of what Lidar technology is, how the actual terrestrial laser scanners work, how the Lidar technology is being applied, not only in construction, but across other facets of data capture, where it be as-built, where it be heritage, where it be conservation work and whatnot. And then the different Lidar methodologies, because within the Lidar scanning sort of family, you have different methodologies on how that technology is applied. And they all produce different results. So hopefully give you an understanding of how that works. And then how to get the best results from your terrestrial Lidar scanner, which is what we were using at Block 505. I then run through the different file conversions and then show you the BIM model fly through and then open to any questions and answers. So hopefully we can cover this very, very quickly. All right, a little bit about me. My background, I'm a land surveyor by training. So I started off my career in Australia. I did all my schooling there. My training as well. I mainly focused a lot of earlier on in my career around the mining business. So I built a lot of mines for BHP. I lived out in the desert for many, many years, scanning everything. So we scanned all the infrastructure. We scanned it for their construction sites. I scanned things for their validation work. I scanned things for procurement processes. We scanned it just to check all the contractors' work to make sure everything was installed according to design. And obviously in the right place in the world. So we have a team of surveyors out there that will do all the set out. We would then go and laser scan and validate that all the installations are done correctly according to the design principles. So that's a bit about where I sort of come from. I moved out of Australia about 15 years ago. So I got shipped over to China to do a lot of fabrication work on the steel modules that were coming in. Main role there again was to scan all the modules before they left China to make sure they were all spatially correct. And we used to do a lot of trial fit inside CAD as opposed to doing it out in the yard. So that's the major difference. And a lot of that stuff was enabled by laser scanning technology or Lidar technology. More recently, I've moved more into the sort of scan to BIM space. So, you know, we scan a lot of objects and then we turn them into BIM models. And that's mainly around commercial real estate and heritage preservation sites here in Singapore. So here's just a couple more examples of sort of where this technology is applied. Here we've got, if you can see my cursor here at the bottom left-hand corner is what we call this sort of like more SLAM technology. The ones that you see that anything that's on a tripod is more terrestrial laser scanning technology. Both use Lidar as a base in terms of where it sends out a laser beam and then get a return signal. All right, so to give you an idea, Hollywood sort of painted a great picture of what Lidar can do. So I remember watching this movie called Iron Man back in 2013, where, you know, someone's had a crime scene, obviously, so he's gone out there with a little scanner and he's scanned the scene and he's managed to recreate the scene. So as you can imagine, the benefits that sort of come with this, you know, Tony Stark doesn't necessarily have to be there on site anymore to walk around the site. He's essentially digitized the site and he can view and interrogate the site from any angle, you know, turn it upside down, rotate it, and really just figure out and, you know, and understand what is happening there on site without actually physically being there. So a lot of these technologies can be enabled, a lot of these visualizations can be enabled, provided the data is digitized correctly and it's accurate. And that's the whole basis of the LiDAR sort of technology itself. So it's mainly used, or I've used it mainly in areas that are dangerous. So we've done like offshore rigs, high buildings. So in any situations where I don't have an as-built, so all my as-built information is missing, I would go and do a laser scan. Areas that are dangerous, so we have to build scaffolding and climb all up and down different things with a tape measure, I would probably do laser scanning as well. These are the two main drivers for laser scanning in sort of these environments. Particularly in offshore rigs, it's very expensive to send engineers out there all the time to revalidate measurements. So the idea is that you send a team of surveyors out there that would go there, spend maybe 4 to 6 weeks there on the rig. They scan everything and then bring all that data back to the office where we can do the engineering work from the comfort of air conditioning back at HQ. Is everyone okay up to this point? Do you need me to clarify anything? Nope. Okay, fantastic. All right, so just to reiterate, we use a lot of laser scanning or LiDAR when as-built information is not available, when as-built information is not accurate or incomplete. So if your as-built information is missing or you don't have doubts about it, then you go out and do a laser scan. Again, when it's too dangerous to do it, it's too complicated. So some things just can't be measured by hand or traditionally. Like if you look at a lot of those oil and gas sites or mining sites, they're just too difficult to measure traditionally. Then you go out there and do a laser scan. And usually when you need fast, accurate results, you do laser scans. One would argue that laser scanning is expensive. The truth of the matter is, yes, it is. It is more expensive in comparison to sending someone out there with a tape measure or a plumb line, but it is more accurate. So it depends on really what your use case is. So if you find that it's going to take you, 3 months to go and measure something, where you can finish that with a laser scan in 3 days, then if you just weigh up the costs, then it probably makes more sense to go out doing a laser scan as opposed to sending out multiple people out there on site. All right, so the picture that you see here on the right is a laser scan. So what does LiDAR actually stand for? It's what is written there. It's light detection and ranging. So you'll hear a lot of terminology being thrown around in industry. One's called 3D laser scan, one's called LiDAR, one's called laser scanning in general. All of these basically mean the same thing. But the official name for the actual technology itself is LiDAR. So light detection and ranging. So it's a method of using sort of remote sensing. So what do I mean by that? It emits its own laser source. So it sends a laser beam out of the device that you're holding. It'll react to the surface and give you a return signal. So unlike your camera or digital cameras, whereby you're relying on light to come into the sensor, laser scanners emit a light source, and then the radiation sort of comes back. All laser scanners pretty much nowadays, all the newer ones at least, are all class 1 laser, so they're completely eye safe. They share the same spectrum as visible light, so you don't need to worry about being poisoned or hurt by any of the lasers. You'll be perfectly fine. One good thing about it too is that it can work in complete darkness, because unlike a digital camera that requires a light source to reflect off the surface and then into your sensor, the LiDAR basically emits the laser source and comes back. So we use it a lot in MEP projects, whereby you need to get information in the plenum and there's no light up above the false ceiling. So we send the laser scanner up and do the scans in there. So is laser scanning safe? The answer is yes. This is the spectrum here on the right hand side, as you can see in the picture, of all the different laser scanners in the market. The ones that were used traditionally were class 3R, and your old total station, the ones that the surveyors use that have a little telescope, they send out a class 3R laser. So laser scanners used to share the same laser spectrum as the total station, but now they've changed. So if you're picking up a laser scanner that's probably more than, I'd say, 10 years old, there shouldn't be many around nowadays that are more than 10 years old. They'll be using a class 3R, but everything that's built from about 10 years ago to now, so 2015 to now, all class 1. Basically every single one that I come across, they're all class 1 lasers. So that's the most commonly used. If you're looking at any laser scanners, I would still ask the question, because it's not an industry that is regulated, whereby there's a regulated body that says all manufacturers must use class 1. I'm sure there's still manufacturers out there that still use a class 3R laser, but all the reputable ones that I've come across are all class 1. So that's something that you don't have to worry about. But I would still ask the question anyway, if you were going to buy a laser scanner, or if you're going to procure the service from somebody. The reason being is that, obviously proper safety protocols must be put in place to preserve the safety of members in public, and probably yourself as well, if you're going out there to either do the work or supervise the work. So it's good to be on the safer side. And it's just a very, very simple question. Just ask for the validation from the hardware manufacturer or the service provider. Okay. So how does LiDAR actually work? This is a little bit more technical. So essentially what happens is you have a box. That box is the laser scanner itself. It sits on a tripod. And this is going back to your traditional terrestrial laser scanning techniques. So the box that sits on a tripod, it sends out a laser beam, and then it reacts off a surface. And then the light is reflected back to the box. So what it does is it measures the time of flight. So it measures the time it takes to emit the beam, reflect off the surface, and then come back. It also measures the intensity of the return signal. So if it's a dark color, then the material will absorb more of the laser. If it's a lighter color like white, it will reflect almost all the laser. So we also measure the return signal or the intensity itself. Then you get an X, Y, and Z position from the laser scanner itself. So a laser scanner, whenever you turn it on, it will always be 0, 0, 0. And then it'll shoot the laser out, hit the surface, and then come back. And then you get an X, Y, Z coordinate of the surface that it hit based off your 0, 0, 0 coordinate. So it'll automatically calculate that point. That's what we refer to as the basics of laser scanning. Now what happens is the laser will then rotate 360 degrees in the horizontal, and then 330 in the vertical, and then it'll shoot laser beams everywhere. And all those laser beams become a collection of dots in space that form what we call as a point cloud. All right, so a point cloud is the output of LiDAR. So when we talk to people in the industry, or you want to write tender specifications, they're two different things. So LiDAR is actual technology that's being used. Point cloud is an output from the LiDAR. You can get point cloud from other capture devices, so you got to keep that in mind. So just because you have a point cloud doesn't mean it always comes from a laser scanner. It could come from a drone, could come from photogrammetry, it could come from a raft of any other technologies out there, like a Matterport or anything else. They also output point clouds. So they're not necessarily the same thing. Just the output format is the same, but the content is a little bit different. All right, so what is a point cloud? A point cloud is basically a giant, what you want to call it, a cloud of points in space. So what you're looking at here on the right-hand side is a building I scanned for NUS a couple of years ago for heritage preservation. It's not an image, so they're all 3D point clouds. So there's a high level of fidelity of the data there. You can rotate that data around, go through it, fly through it, interrogate it, even 3D print it if you wanted to. All that is possible from that accurate digitization. So we set up the scanner very, very close to the object, and then just scanned it. What you're looking at there is X, Y, Z in combination with RGB and intensity. So the RGB values come from a digital camera that is built into the device. So the device is a digital camera that is built in. It takes HDR photography after you scan, and then stitches all the data together. So when it writes that one data line, it'll write it as this is a data point. It'll have an X, Y, and Z coordinate, so you know where it is. Then it's got an RGB value, so you know what color that dot is, and then an intensity value if you want to turn off the color. Okay, and the intensity then is measured by the material of the surface it's reacted off or it's reflected from, if that makes sense. Is everyone okay with this concept before I move on? Okay, no burning questions? All right, good. Okay, so Lidar forms the most accurate sort of base data set for everything. So from an accurate point cloud, all right, using Lidar technology as a method of capture, you have a very, very high fidelity data set that can be turned into virtually anything. So you can start doing BIM modeling from it. You can turn it into an AR, VR experience. You can do all that Gaussian splatting stuff that you've seen all over the internet, whereby you can fly through almost a near realistic, job site, so to speak, or a near realistic site that's been scanned and photographed correctly. All this stuff is possible, provided that you have an accurate data set. So the question is, how do I get an accurate data set? How do I use technology to make sure the data is accurate? So hopefully I'm going to be able to teach you some of that today. Here are some of the popular brands that I've used in the past. So I've used the Leica, Trimble, ZNF, Faro, Regal. These guys are probably they've dominated the entire market. So about 90% of the market will use one of these products, particularly a Leica system. So Leica, Trimble, and Faro are probably the most popular tools in the market today in terms of terrestrial scanning and SLAM technology. The Regal scanners are very specialized. They're more for airborne laser scanning and roads. So if you want to do mobile mapping where you mount it on a car, they're more specialized in those sort of devices. And the ZNF scanner basically was the old OEM for Leica, Trimble, and Faro. So everyone used to buy the actual scanner from ZNF and then just rebadge it as a Leica, Trimble, or Faro, and then build a workflow around it. But the actual hardware is all from ZNF. So these are the 5 main sort of drivers. There are a lot of companies popping up out of China that I've seen. I haven't used any of their scanners to date, but I have seen on the internet that there are some good results, but I haven't tested it myself. So the only difference is in why I mentioned a lot of these China products is that they come in at about 20% of the price of one of these well-known brands. So in terms of a cost comparison, it's definitely something worth considering if you're looking down the line of buying your own. All right, so what are the differences between the laser scanners or LiDAR devices? So the highest level of accuracy is always going to come from a terrestrial laser scanner. So that's the highest level of accuracy you're going to be able to achieve. And these come in 2 categories. These come as engineering grade or high precision. So engineering grade would be plus or minus 1 to 2 millimeters in terms of precision. High precision scanners are in the microns. So high precision are like laser trackers that they only use mainly in manufacturing. So when you're manufacturing car chassis or aeroplane wings, and they want to scan to make sure the NURB surface is completely aligned, to make sure all those pieces are aligned, then they use a high precision scanner. I have not seen to date anyone use a high precision scanner for engineering because it's completely overkill. And they cost about 3 times more than a normal engineering grade scanner. For most applications that I've used in my career, engineering grade scanners are more than enough to cover 99% of your jobs, applications that you require in the construction and engineering sort of space. The other laser scanners that are out there are car-mounted laser scanners. So we call these mobile laser scanners. They sit on your car and you can just drive at 110, 80 kilometers an hour, whatever it is, and you scan the road surfaces, the pavement. It's good for road construction, road as-built capture, things like that. You have then airborne laser scanners as well. So if you're familiar with Virtual Singapore, they've been using airborne laser scanners for the last 20 years. They capture all the across all the country. They just fly over the top of the aeroplane, and then they shoot lasers down to capture all the buildings and all the facades and everything, basically everything. They just map everything from the sky. It's really good for flood studies, for mapping like large towns where you need very, very quick asset or data capture that is accurate. And then you have SLAM technology. So SLAM is more of a newer technology that sort of came into the market in about 2015 or so. So it's been around about 10 years. And this is really around how do we combine the best of both worlds, whereby I can get a small device and walk and scan at the same time. And I'll show you some examples of each in a second. And then the last but not least is drone photogrammetry. So this has become really, really popular lately as well, because the camera sensors inside drones have improved drastically, which allows you to do photogrammetry from the sky. to get fairly accurate results. Okay. So these are the differences in the laser scanners. The price also ranges from left to right. So the cheapest one would be on the left, the most expensive one is on the right. The first three are engineering grade terrestrial laser scanners. The one on the very right, which is a Leica ATS600, is a high precision scanner. The first one that you see on the left, which is a Farad S70, is what we call phase-based, so they don't have very long range, whereas a Topcon and the Leica P40 are pulse-based scanners, so their range can exceed 300 meters, whereas a Farad S70, as the S suggests, it's only up to 70 meters. But for most applications that I use it for, 70 meters is more than enough. I'm not scanning mountains and I'm not scanning anything that's really, really far away. A lot of the projects we walk into are, I'll scan like a shed or anything where 70 meters is definitely more than enough in terms of the range that I need. This is what we call as a mobile mapping device. So when I was still working in Australia, I did a lot of mobile mapping work on the highways. We just mount one of these on the car and we just drive along the highway. We can survey up to 20 kilometers per day. So in the past, 20 kilometers used to take us about a year to survey. We had to close the road, do it manually, run out there with a stick and a mirror and then take the measurement. But with one of these now, I can measure 1 million points per second. Just drive past 4 times, and 20 kilometers a day is not a big area to cover with one of these devices. Just as a bit of trivia, SLA actually own one of these devices, and they map the Singapore roads quite regularly. Basically on a daily basis, they're driving around with one of these devices on the back. They do that to keep virtual Singapore up to date and to make sure they can map any changes that happen in Singapore, because our roads are changing all the time, and they want to get ahead of that. So they're continuously mapping and making sure that things are exactly the way they should be, and capturing any changes that have happened along the way. This is airborne technology. So this is how this one works. So basically a scanner is mounted on the bottom of a plane. The plane just flies and does a sweep of the entire site. So as you can see, it's very, very fast. It's not obviously going to be as accurate as an engineering scanner, as an engineering grade terrestrial scanner, but for the amount of time it takes and for the purpose of what you're going to use the data for, it's pretty good. You're not obviously going to get down to the millimeters, but you're looking at something like 100 to 200 mil is definitely something doable for airborne devices. This is what I was mentioned earlier around SLAM technology. So you'll probably see this at a lot of geospatial conferences. They like to have these little laser scanners mounted on the Boston Dynamics dog because it's really cool. These are very, very good, but nowhere near as accurate as a terrestrial scanner. So the best accuracy you're probably going to get out of this is 20 millimeters or 2 cm. And that's really pushing the envelope already, depending on how you're going to run your job site. So if your job site is very, very large and very complicated, this will not be able to do the job. You have to revert back to an engineering grade terrestrial scanner to make sure that when you scan your entire site, that the site is accurate. Last but not least, here is the drone technology. So basically, you have cameras mounted on the bottom of drones. The camera sensors have improved dramatically since then. Since I started looking at it. So nowadays you can even fly a small DJI Mavic or DJI Air even, and still get very, very good results. It works by taking multiple images. So it's not actually sending out a laser beam to react to the surface. It just takes an image. But there is enough overlap between the image to ensure that you can do a triangulation, and then from there you can derive a 3D point. All right. So the main difference as to what you need to look out for with photogrammetry is because it's not a direct measurement, the measurement is derived, which means that you may have a problem with scale. It may not be exactly 1-to-1. So in order to control this, what you need to do is put ground control in. So usually you'll see the surveyor will put out maybe like a small paper target or a small target on the ground that have, you know, red, that are black or white, and then they go and survey that with a total station. So they have a baseline as to between these 2 points, this is an exact distance, and then they use that to scale the photogrammetry model. That's how we circumvent that problem, because you can't guarantee that it's a one-to-one measurement. Whereas with all LiDAR technology, it's always one-to-one because it's direct measurement. So this is an introduction into your terrestrial laser scanners. So this is the one that we used at 505. It does 1 million points per second. It's a Faro Focus S350. It has 360-degree view, 330 in the vertical, and you can measure up to a distance of about 350 meters. They're very robust, very portable, and very, very fast. So one scan is about 3 minutes, and then you just pick it up and move on to the next point. So how do I pick the right scanner? I've used almost all the scanners in the market, at least the popular ones. And I consider that these are my sort of go-to list if I'm going to go pick a scanner that I'm going to use every day. So I would consider the weight. Some of the scanners, like this RTC 360 from Leica, is built from some sort of aluminium or a metal, whereas a Faro is mainly plastic. The weight difference is enormous. So one weighs about 7 kilos, no, about 6 kilos, and one weighs just under 4. So it may not sound like much, but when you're picking up the scanner about 200 times a day, it starts to be a little bit taxing on the body, especially when you're walking up and down stairs all day, all night, whatever it is that you're doing. You know, the extra, 2-3 kilos that you're carrying becomes very, very taxing. So I like to pick something that's a bit lighter. The shape is something that I would consider as well. I like things that are square. So this RTC 360 is square. This Faro scanner is square. And the reason why I like it to be square is when I take the scanner off the tripod and put it on the ground, I don't want it to roll away. Some of the other scanners, like the Regal scanners, I like them to be circular. These scanners will roll away, and when it rolls away down the side of a transfer station or down the stairs, you've just lost an $80,000 machine. So square is good because I know when I put it down, it's going to be in exactly the same spot as where I left it, and I'm going to be able to pick it up and put it back on. It's not going to slip out of my hands because there's a lot of things to hold on to. All right, so squarish scanners are the ones that sort of I prefer. One other thing that you want to consider is the size of the output file. So the Faros like this, they produce an output file that is about 100 megabytes per scan. Something like a RTC 360 is in the range of about 1 gigabyte per scan. So if you think about it, if you're scanning roughly about 80 scans a day, having to move 100 GB of data per day to a computer and then start processing is very, very time consuming. So you want to pick a scanner that has a way of compressing the data files to the smallest common denominator. That way I can move the data off the machine very, very quickly and then start processing the data somewhere else and not having to hang around waiting for the machine to finish copying and then to start my work again. The last three are probably not as important as the first three because all the scanners are pretty much the same nowadays. All the resolution speed is about the same. They all do the 5 millimeters at 10 millimeters, 5 millimeter spacing at 10 meters away. All this resolution is pretty much the same. The scanning speeds are pretty much the same nowadays. All the scanners are doing roughly 1 million points per second. The RTC 360 is currently still the fastest scanner in the market. This one does 2 million points per second. So I do like the RTC 360. It's very, very quick. The only downside is the output file and the shape and the weight. But depending on what you're doing, if you want to be there quick and collect heaps of data really quickly, then it's definitely the machine to go to. The other thing you want to consider also is whether it's phase-based or pulse-based scanners. The RT360 that you're looking at here is a phase-based scanner. Same with the Faros, they're all phase-based scanners. They're faster, but the data is more noisy. Okay, so you do get a lot of you get more errors in your data set as opposed to a pulse-based laser scanner. Pulse-based laser scanners are slower, they have longer range, but the data set is cleaner. For 90% of the applications that I use it for, laser scanning for, I'm happy to use a face-based scanner, because even though it was not as clean as how I'd like it, it's clean enough for almost all my use cases. And all the pictures I've shown you to date are all done from a face-based scanner. So naturally, you probably couldn't tell the difference anyway between the two data sets. All right, so a lot of technology has already been placed inside the software of these devices nowadays to make them super simple to use. If you look at the RTC360, it's only got 3 buttons: low, medium, and fine. So if you just select low, it just means that it's a quick scan. Medium is a normal scan, and fine is a high resolution scan. And that's all you can do. So you just press either one of those 3 buttons. There's no fiddling around anymore, and then most of the software now will take care of all the combination and what we call is least squares adjustment mathematical calculations. But that doesn't mean that you don't keep your survey principles in mind, because just because the software can do a lot of the stuff doesn't mean it doesn't fail. It fails, and it does fail often. So you do have to keep in mind survey principles in order to control the errors that you will get in your data set. So what I mean by survey principles is make sure that you cover enough distance, make sure you have enough overlap, make sure what you're scanning is not too far away, things like that. Just very basic understanding, not just turn it on blindly and just hit scan and just keep walking and scan. Have a systematic sort of approach. The best way to do it, if you really just want to do a process style scan, is just to set up a grid system. So I would just scan maybe every 5 meters, and then it's a sure way of not failing any project at all. But it means that you're going to be over scanning some areas, but it means that you'll be guaranteed a very good result. So if your area allows it, just scan every 5 meters, up and down like similar to a grid line. Wherever there's an intersection, just scan. That's probably the best way of looking at it. Okay, so survey datums. Why do we need them? There's 2 forms of accuracy. The scanning manufacturer will specify precision on the device. When you do register your data, you will get an error that is calculated. That is what we call is a local accuracy or local datum, because it's within the scanning environment itself. And then we need to move it to a survey datum, if required, or a global datum. And that is sort of where it sits in the world. So if you think about it, if you make a car, how the car is developed and how well the car is made is what we call is the local accuracy. And then where the car is parked in the world is your global accuracy. And that's where we need the survey data. Sometimes we need to place the building in relation to other buildings in the world. And you need a surveyor to go and do that to get the survey coordinates of the building corners maybe, or things that are overlapping in your site, and then coordinate it and then move the entire data set across. So when people talk about accuracy, there's always in 2 forms. There's either local or global in nature. All right, I'm just a bit weary of time, so I'm just gonna maybe move a little bit quickly and not explain so technical about this stuff. Just a basic concept. When you do laser scanning is not X-ray, okay? It is not X-ray. So sometimes people think that, oh, how did you get that? Oh, it's because I scanned from a position where I can see it. So the rule of thumb is, if I can't see it, you can't scan it. Okay, it's not X-ray. So if you need to scan something that you can't see, then you need to find a position for the scanner that it can see that object. But it also needs to be scanned in a way that you can still see the previous scan. So then you can join the data. So if you can't see the object and you can't join it and you can't see your previous scan, then that object can't be captured, because you can't, even though you move it to the other side and you scan the object, you can't join it back to the main data set. All right, so that's what this sort of basic understanding of this slide means. Okay, so there's 2 forms of registration. So when we do all the scanning, there's 2 ways that we can bring the data together. So as you can see here on the right hand side, this is a data set that is scanned from about 30 different scan positions and is joined together to form one model. We do that in 2 ways. There's 3 ways really. There's targeted, there's cloud to cloud, or there's a blended approach, which is a combination of both target and cloud to cloud. So cloud to cloud means I don't put any targets out. So I don't put any survey targets. I just use the the common features that I have on site to bring data together. So things like walls are very, very good to use because walls give you a plane, and then the machine then just finds patterns inside the data to match. So they match the walls, they match the floors, they match corners and things that are flat in nature to overlap the data. The traditional way is to use targets. So I can put a target out, I give it a target number, I scan the target, and I scan the target from another scan position, and then I join the data that way. Or the blended approach is the way that is popular nowadays, is just to do a cloud to cloud if the job is small, and then use the targets to move it to a survey datum. That's the difference. Okay, so these are what targets kind of look like. So you need at least 3 targets as a minimum in each scan. It can either be a sphere, like a paddle target, or like a bit of paper that you put out that looks like that. It is very, very slow in the field, so you're probably going to increase your capture time by 2-fold, but it is more accurate, and it's it makes managing very complicated large sites easier. So that's where you sort of got to make the decision. Okay, if I go with a target sort of scanning, then it's going to be slower on site, but it's going to save me effort in the office, and I'm going to be guaranteed a good result. Or do I go with cloud to cloud, which is going to be really, really quick, and then save me, increase my office time, because I have to start, finding patterns and things, surfaces in the walls and stuff like that, that'll help me put the data together. So my answer to that is, if you've got a large, complicated project, definitely use targets. If you've got a very, very quick project like this block 505, which is small and easy to do, don't use targets. Just use cloud to cloud. It's going to be more than enough to get the data to merge correctly. Okay, most errors in laser scanning happen because of error propagation. So when you set up a scanner, you're always going to introduce minor errors, and these are inevitable. It's impossible to control all the errors. It's almost near impossible. So most of the time when you have problems, it's due to error propagation. And this is where your traditional survey techniques sort of come into play. So the things that you need to make sure of is that you make sure you have sufficient overlap between scans. So make sure you have about 60% overlap between scans. Make sure you can see multiple targets between scans. And then make sure you don't scan too far away from your previous scan. And then if you do all of those 3 things, you should be able to control how badly the error propagates throughout your project, and then end up with a better result. Okay, this one here, sometimes when you scan objects like corners or piping, you do get this thing called spray. These are mixed pixel errors. So a scanner will send out 1 laser beam but get like 3 or 4 returns. And this happens because part of the beam hits a corner, and then it thinks that there's more data, there's more surfaces beyond that, and it reflects multiple returns. It's just a phenomenon that happens with the technology. Most of the software will try and eliminate this, but it's not perfect at doing it. So when you're going through and you're looking at your scan data and you see a pipe that has like these weird a weird tail that comes from it, you just ignore the data because it's not actually there. There's no object there. It's just an error that happens with laser scanners in general. All right, here are some other popular tools that I've seen in the market as well. So here's a Matterport Matterport scanner. This is not a laser scanner. It's a camera, so it's not as accurate as a terrestrial laser scanner. You definitely cannot do a whole building and call it accurate for engineering design. The one on the top right-hand side is what we call a Faro Freestyle. These are not laser scanners either. These is what we call a structured light scanner. They use light and imagery to create 3D point clouds. They are accurate though. They're mainly used for artifacts, but they cannot be used to scan buildings. They're good at scanning historic artifacts and things like that. And then obviously the bottom right one is a mobile device scanner. These are not accurate at all. So if you're only doing like a small room, then you can use one of these. You'll probably get anything close to about 2 cm, but I wouldn't use it for anything else. It's just a gimmick. Okay, so this sort of gives you an idea of sort of where the technology sort of lies in terms of accuracy. So if I was doing a small space, there would be not much difference between terrestrial laser scanners, SLAM technology, or photogrammetry. If I was doing a simple floor plate, the terrestrial scanner will still be quite good. Whereas, as you can see, the accuracy of the SLAM and the photogrammetry will start dropping off. Anything that's got to do with a multi-story building, it starts dropping off even more. Large buildings, dropping off even more. And a full building scan, I'm talking maybe like 30 floors, inside, outside, every single room. There is no way you better use photogrammetry or SLAM technology for any of that. I would definitely just be using a terrestrial laser scanner for any of that work. So as you can see, terrestrial laser scanners sort of account for like 90%, 95% of the entire sort of application that you have there. All right, these are just some samples, but I'll run through the 505 in more detail. Okay, so these are the different point cloud conversions. So these are very, very popular point cloud types. So depending on what software you're using, you'll be able to output any of these formats. PTS and PTX are mainly used by Leica. E57 is probably the most common that you'll probably see out there. And what I mean by E57 inside the file will carry your XYZ intensity, RGB value, and vector from the scan origin. Right. So whenever you have a chance, you always just want to export out as E57 if the software allows it, because that will basically go into almost any software. It's very, very universal. Sometimes you'll see like LAS. That mainly comes from SLAM scanners. They usually use LAS. And then if you see an LAZ, it's just a compressed LAS file, which you just have to uncompress and it just turns to an LAS. The Autodesk format is RCP. So Autodesk products only accept RCP file. So how do I get an RCP file? Right. So this is the process. To use scan data in Revit, the point clouds need to be converted to RCP. The process is quite simple. So you export the point cloud from your scanning software in E57 format. So whether you're using a Faro software or a Leica software, E57 format is probably ideal. And then you want to import that file into Autodesk Recap. Once you import that file into Autodesk Recap, it'll automatically convert it to an RCP file. So RCP is not a database, by the way. It is not a file, it's a database. So what happens is you get an RCP file in your folder, and then you get a subfolder called support. And inside that support folder is all the files that the RCP needs. The RCP is just a header for the database. That file is just a header for the database. So when you copy it somewhere else, you need to copy the entire thing. Don't just copy the RCP file. All right, you'll see an RCP file is only a few kilobytes. That's not a point cloud. It's definitely not the right file. So you want to copy that entire thing, including the support folder, to wherever it needs to go for you to then consume in Revit. There are options to export an RCP directly out of the scanning software that you use. The only reason I don't suggest doing it this way is that it's not very quick, and sometimes I get errors in the data when I export directly from the scanning software. So as a foolproof methodology, I always just export out as E57 because it exports out of the scanning software very, very quickly, and then import it into Autodesk Recap because it converts it very quickly, and I know it's always going to work. I've never had a dataset fail on me when I do it this way. Whereas if I convert out of the scanning software directly into Recap, sometimes I get things that fail. Okay. Here's a sample of the point cloud that we captured. But what I'm going to do is I'm going to try and log in using my other computer. This works, and then show you the actual model inside the Faro software. Just give me a second. So everything's slow when you're running point cloud software. Oh, that's another thing I forgot to mention. You need to have a fairly powerful machine to process point cloud data. Because the data sets are so huge, you'll definitely have a problem processing on underpowered devices. So you'll need something like at least 32 gig RAM, very substantial video card if you want to have any chance of processing it very quickly without crashing. So I'm running at the moment a 32 GB RAM and a 4 gig video card on my laptop here that's processing this small data set, and it's already choking up my PC. It won't let me open up Microsoft Teams. Sorry, Shara, can you admit me?
Yes.
That's me again. Okay, I'll share on this PC. Everyone see that? It's coming.
Yes, no.
Okay, so this is the result of the scans. So as you can see, it's high fidelity. I can see everything. So the fans, all the joins, your louvers, all the detail is there. Even the people standing around, all that data is there. I can go to the next scan, see what's going on here. Give it some time to load. So you can see all this data is captured really well. So from here, what we do is we take this point cloud data and we then convert it into a BIM model. So the process of converting into a BIM model is no different to creating a BIM model from your 2D drawings, for example. We use the scan data as a base reference, and then we just trace over the top of the scans. Similar to how you do GIS back in the olden days, where you have, like, say, a light table where you have just an old drawing that's being projected through the light, and you just trace over the top. We do it exactly the same way. Sorry, it's just very slow. This is choking up the PC. Because there's so much level of detail, we can see a lot of things. Like we can ascertain what the member sizes are, and then all it is just selecting the right member size out of Revit and just tracing over the top, and then just following the line of the beam. So one thing you got to bear in mind is that when we do work inside BIM, like, we try as much as possible to follow the as-built as much as we can, but then we also have to keep in mind too that this element needs to be a single steel member. So typically how we model it is we just model it from end to end. So we just take the two ends as being accurate, and in between is just a straight. Unless there is a specific requirement for us to actually model the bending if there's a defect on the structural member. And in that instance, what we do is we just model in two member sizes, and just make note that there are two member sizes there. So when you do a takeoff, it's going to account for an extra one, because there's no other way to model it. Okay, so that's what that data set sort of looks like. Once we go from the point cloud, when we convert it to BIM, the final BIM model looks like this. So I'm just going to stop sharing here. I'll share back on this one. The final BIM model looks like this. Okay, so here you can do your walkthrough. And it's the same site. Okay. So all of these structural members were traced off the point cloud in BIM. So what happens is when we reference in the point cloud into the BIM model, you can see the point cloud inside the BIM, and then you can slice and dice it, do your sectioning in whichever angle that you want to see in order to position all these member sizes correctly. And then we just draw it in. Okay. Okay, so I might open it up to, we've got about 10 minutes left. I might open it up to any Q&A if anyone's got any questions or any clarifications that need to be addressed.
Do you have any questions?
So usually, what's the size of your point cloud model?
The size of this point cloud model, from memory, it was about 20 GB from memory. But once I export it out to that's the entire project that I have, so including all the raw files. But once I export it out, it's about one gigabyte, and then when I convert it to a recap file, it was about 800 megabytes.
So the uploading time you need to take longer, or just a short period can?
For uploading?
Yeah, your uploading file. When you
No,
upload the file, right?
I mean, here in Singapore, I can upload that file in about 2 minutes.
Wow.
Yeah, 800 megabytes is not a problem. It's you see the loading of the point cloud into your PC. 800 megabytes is not it's not that big. Like, you don't need a crazy computer to handle that. Any standard Revit machine should be able to do that. But if your point cloud files are getting like to the point where it's like 5 GB, 10 GB point cloud files, then you want to go back and then ask your survey vendor to break the files up into smaller files. So either by like a zone, or by floor, or by something logical, to make it more manageable. Because you don't usually you don't get an entire floor that is 30 or 40 gigabytes. That's just too much data.
Oh, okay. Thank you.
Yeah.
Hello, Richard. Hi,
Yep.
here.
Hi.
Yeah. Richard, would you tell me to when we import it to the model, Revit model, can we able to position it according to the service point locations?
Yeah, you can. So there's two ways of doing that, kind. So
Yes.
you either do it and you move the point cloud. So when you issue the point cloud, you issue it already in a survey datum, or you can just change it in your survey datum inside Revit. So you just set your real world coordinate in Revit, which can be done. What you need to keep in mind is that you do need the survey coordinate. So typically, what you can do is if you're getting a survey done properly in the survey datum, what you do is you go out to the street and you get a land surveyor to go out there onto the street and bring the survey coordinate in from a SVY21 marker, where they have a token, a coordinate, and then bring that survey in, and then use targets to do the laser scan. And then your laser scan data will be coordinated from the beginning. The shortcut way of doing it is just to do the laser scanning using the way that we did it, and then moving it later in Revit by either coordinating it from a building corner or something that is common, that we have a coordinate for. But we need a coordinate for other building corners and whatnot.
So in our case, we use option 2, is it?
Yeah, that's correct. So I still have to move it. I haven't had a chance to open that drawing yet. But yeah, when I have a look at it, I'll let you know. But yeah, it would be option 2 for that.
Okay. Thank you.
No worries. Any other questions?
I have one. Yeah, I have one more question. Just now, you mentioned that the data can be extracted from the software. It's not as a recap versions, right? So
Sorry, I didn't find
and then
with that.
sorry, just now you mentioned that the data was we can get the data from the device, and the one before we import it into the point cloud model, you need to do some calculations, right? The manual calculations.
Yes, so there's a couple of ways to look at it. So what happens is when you import the data into the software for the first time from the field, all your scans are always 0, 0, 0. So say I scan 5 positions, all of those 5 positions, the scanning origin is 0, 0, 0. So all the scans will be on top of each other. But in reality, they're not in the same position, right? So what happens is you need to tell the software that to do a registration, so do a least squares adjustment for these scans. So there's a couple of ways you can do it. You can use your target methodology, whereby I'll put targets out and then select the targets inside the scanning software to say that this is target A from scan position 1, and this is target A from scan position 2, this is target A from scan position 3, and then use that to then position your actual laser scanners, your scanning positions. Or sorry, I'm just getting a lot of phone calls for some reason.
It's okay.
Or you can do a cloud-to-cloud registration. So cloud-to-cloud registration is basically, it looks for patterns in the scan data. So things like this wall here would be a flat surface. Things like this wall here would be a flat surface. This wall here would be a flat surface. You know, this concrete here is a flat surface, which is nice. It'll look for patterns like this. So what the software will then do is it'll do a top-down slice, and it'll say, okay, I know this is a wall, and I know this wall is common in 3 or 4 scans, and I'm going to use that as a scan target automatically. So you don't need to tell it that unless there's a problem. So firstly, you just let it run automatically, right? And it'll give you an answer, and then you just validate your answer. You just check it. So you check in the software that, is this wall actually the same wall, or do I see 3 or 4 walls? If I see more than 1 wall and I know this is only a single wall, then I know that the automatic method didn't work. So then I have to go back to the manual way, which is actually selecting the wall and saying this wall is the same as this wall is the same in this scan, and this wall is the same wall in this scan. And then the software will go, okay, now I understand, and then it'll do the registration for you.
Okay,
Yeah.
thanks.
No worries.
Thank you.
No problem.
Do you have anything else to ask?
Sorry.
I think we don't have any questions.
Sorry, I missed that. Was that a question?
No. I think we don't have any question for.
Oh, okay.
Sorry.
No problem.
Sorry.
Okay. All right. So thanks everybody then. Thank you for your time.
Thanks for your time today, Richard. Yeah.
Not a problem. If you have any other questions, just let me know. I think Shara, you got my contact details anyway.
Thank you, Mr. Richard.
Thank you very much. Okay.
Take care,
Bye
everyone.
now.